equation that's got a lot kind of going on. So let's see if I can find a good example of a funky one. Let's see. Yeah, all right, let's do this. All right, so if we have this function, I'm trying to find its root, and we use as a guess 1. 1 doesn't seem so terrible. 1 minus 3 is negative 2 plus 6 is 4. I mean, that's better than it being 170. 4 is relatively close to 0. I mean, it seems reasonable. So let's see what happens to this poor little dude. F prime of x. Some of you guys might pick up on this, or not. What's f prime at 1? 0. All right, so let's take care of that. Let's use something close to 1. Does everybody see that? What's happening? Where's f prime in the algorithm? On the bottom. So you can't use something that's 0, obviously. So let's make this 1.01. Let's see what happens. So I got my function, so now what I have to use is answer minus answer cubed minus 3 answer plus 6 all over 3 answer squared minus 3. So let's see what happens here. So my initial guess is 1.01. Let's see what happens. Answer minus answer to the third. Minus 3 answer plus 6 divided by let's see what happens. Okay. Let's see if it might be able to recover. Yeah, it looks like it's recovering. That's a good example of like a bad guess, just making it take longer than it would. Let's try with 0.99. Oops. Yeah, it's going to come back too. I like it. So it looks like the right... Ooh, is it going to work? Ooh, look at that. Look what's happening. Oh, that was interesting for a minute. Let's try that again. 0.99. So watch, it looks like it's steadily marching towards the right answer. Look at that. Look what happens. Went to 0.9 and then went to 7. 5, 3, 2, 1, negative. And then it bounced back to 2. 1. And then it bounced, holy shit. Sorry. So let's see. Let's look at this thing. X cubed minus 3x plus 6. Okay. Change that. Oh, I don't need a 2. delete. Delete. Plus 6, right? Yeah, so see how the slope right in here changes so drastically. See, so this, if I had a, let me zoom in a little. Oh, I can use this one over here. That would be so much better. I could even use this screen over here. That'd be insane. All right. So my guess was this. The tangent line would take me here, right? So my guess is like this. The tangent line would take me to here. Where's this tangent line take me? Back over there. That's the bouncing we see. Until it gets to a point where it's like you're here and that tangent line takes me here, and now it's going to start to zoom in on this. So remember, there's the more twists and turns that are happening close to the root that you're trying to get to, the more bouncing there might be, the more you might actually end up with something that never hones in on anything. So here's that -1. You see that's a horizontal tangent line? Yeah. And then here, if I did 0.99, it took me way back somewhere. And if I do 1, where was I? What was it? No, here's the 1. It was the 1 here, right? There's the 1. If I used 0.99, it took me way over there. If I used 1.01, it took me way back there. Because right here, it's horizontal. So a little bit this way, it's just barely not horizontal. So if I follow that, oh shit, I'm going to be way back. It was -65. Okay. And the bouncing thing could happen when I have curves near my root. A lot of turns near my root. How you guys? This is a relatively simple compared to some other stuff we've done, but it's a beautiful, quick show of how calculus immediately helps us make better. I point to that because that's mostly my calculators, my phone. Better calculators using these algorithms. And they modified it somehow so that it didn't have as many problems. It definitely has problems somewhere. Let me see, where was it? If I have a function like, oh shit. Oh, it doesn't matter. This is x squared. Let's see if it's able to handle this. Calc. I think it should be able to. Especially because they give it an area to search in. Yeah, okay. But sometimes when the answer is at a place where it turns around, you might get an error saying no sign change. Something like that. So that's a part of the algorithm, the way it works. It's looking for if there's a sign change near the root, and it happens within the interval he gave it to search on. But TI has modified it so it doesn't have as many problems as it could if we were doing it by hand. That's why I was really curious to see what it was, and we know you want to know what it is, right? It's like KFC special strategy, whatever. Okay, is that decent right there? That's basically the idea of Newton's method. They either give you a function, they ask you to find the root, so you know what f is. They give you an equation. So you have a way to figure out a rough estimate of a guess, and then you got to make it equal to 0 so you can see what the hell your f is that you need.
Most of the time we're going to do it by hand, right?
Yeah, in fact, I'd love to ask a question like, give a rough sketch of these two functions and find and see where the intersection is and have that as your first guess. Yes?
And then we could just use the calculator to check our work, right?
Oh, shit. If you got the calculator, I can't stop you from checking everything. Yeah. And, and like I said, this algorithm is not the best by hand. Very quickly it becomes undoable, right? Or not undoable, but very, a lot to work with. That's why this is a beautiful example of the connection between math by hand concept and programming things to do things mathematically. This is a beautiful intersection of those two. A program would just eat the shit out of this thing, right? So It's beautiful. Okay, so there is that section 4.9 that I was considering. We basically have already done it, to be honest, to a certain point. But I am actually completely fine with making that officially on the next test. I think some of you guys have enough homework to try to catch up on tonight anyway, without having one more section to do, so I'm okay with that. 4.9 is antiderivatives, and then chapter 5 is going to be where we actually get into the full idea of integration, which is, we have to actually marry that integration with anti-differentiation. See how they connect. Thank God they do, or else there'd be a lot of shit we could never do. Oh my God. Like, what shit is that? Do I care? I don't know. You didn't tell me. So we can start looking at the practice tests and stuff if you want to. You can work on corrections to the quiz due tomorrow, so you can do that. Everybody's got a copy of the practice test, right? Yes?
I cannot find mine.
Aw. That's my last one. And to be honest, there's several of them I want to do in class because I didn't finish them on the answer key. Because I didn't bring one with me. I think I gave them all away, and then I forgot to print one out for myself for the weekend. I was like, oh, good. So there's I think it's the last three. 57, 58, 59 from chapter 4 review, I think it is. Or is it, where is it from? What's the very last problem? Page
360.
Okay, so it is that one. And it is 57, 58, 59, right? The last three?
Yeah, 52.
Yeah, that one I got down there, but I think for the most part, we'll see.
Yep.
Well, actually, did I finish that one? Oof. Yeah, let's look at, what was the first one? 53? Yeah, let's kind of look at that one. That one gets gross really fast. That one says find the smallest possible area of an isosceles triangle that is circumscribed about a circle of radius r. So who's inside who in this case? Yeah, like, is the triangle inside the circle, or is the circle inside the triangle? Circle's inside the triangle. So this triangle is circumscribed about the circle. So it's going to look like this. Bless you. Wow, I'm trying. There. Give him a little beard. It'll fit there. Bearded circle triangle. It says find the smallest possible area, and the circle radius is r. Now, here's how this one is interesting at the beginning, and then it gets really difficult very quickly. Just to tell you, but where's the smartest place to draw my radius? What is it? What's the areas? What's the area of a triangle? What's that formula? 1/2 base them side, or something. Half base them side, base them side. So here's the height. And here's the base. That's amazing, Jeff. No, so where is kind of a smart place to draw the radius? I can't draw it. The radius is not going to relate directly to the base in any way.
So like drag down.
You see that? Because the radius that we go across, and then how much is left from the base, well, that's a difficult problem in its own.
So use those.
Oh, I see. From the base. like perpendicular to the base. Okay, that would make the most sense. So here's the r. You can even draw a straight line if you want to. Well, let's just stick with this as height, and this is the base. I like it. Why not? So how much is this, for example? What's this? What's the rest of the height?
H minus R.
Yeah, this would be h minus r. I like it. Yes, sir.
Wait, wouldn't it be H minus 2R?
No,
No.
because I did it to there. Now, I could do 2r and then figure that much out.
Okay.
To be honest, that would also work. But it won't quite do what I'm about to do next. Because what's the other thing I need? I need some information about the base here, right? Now, this is what kind of a triangle? I think it says it's an isosceles triangle, right? What's true about an isosceles triangle? These two sides are the same length, right? This side and this side are the same length. Okay. So I've got height and radius related. I probably want base and radius related somehow. I've got too many variables over there, right? I need somehow a relationship either between base and radius, so I can get one between base and height. I need some relationship between base and height. So, what's this here? Radius. I like it. And then, how much is this? I'm going to let you think about that. And think about why I would be curious about that.
It's not an equilateral triangle, so how would you know that that's exactly halfway?
I didn't say equilateral, it's isosceles.
Yeah, I know. Like,
I didn't say it was halfway. Let me make one suggestion. I think this came up the other day. I think you actually had this point. Let's make this what we're talking about. We won't call it B then. We'll call it X. So then the area becomes X times H. Because X is half the base. Is that cool? Now why would I do that? I'm trying to... What is it that I need? Now this one is really freaky, so I understand. But do you guys see what I mean? I need a relationship between the base, the X variable now, and the H variable. I need a relationship between them because I'm missing that tell me. Remember tell me, ask me. That's the function I want to work with. There's too many variables in it. Right? So I need to get a relationship between the two of them. So I'm trying to make a similar triangle here to this one.
would it also be H minus R?
Which one?
Like,
This guy? No, definitely not. I mean, this is R. This is H minus R. Here's the right angle in this. So how would I get this side? I mean, it's a right triangle. So the square root of, h minus r squared minus r squared. So it'd be the square root of h squared minus 2rh plus r squared minus r squared. So that's gone. I like it. So this triangle here is similar triangles with this triangle here. And therefore, h to x has to equal that to r. Oh, let me put it in better form. H squared minus 2rh over r. So I can solve this for x and plug that in, and then take derivatives. All right.
Did you get the 2RH?
When I FOIL this out,
Oh, okay.
yeah. Just because the r squares
Oh, I'm sorry.
cancel. Yeah. So if I solve this for h, I get, for x, sorry, I get RH over the square root of h squared minus 2RH. And I plug this in here, and then I can take derivatives. So I wanted a problem that would push it, that wouldn't tell you something directly. This problem was a bit uglier than the one I really wanted, but oh well. I didn't realize until I started, let me just start doing this. Holy shit, this is a little more involved. That is definitely not the first thing that would come to your mind to do this. But the problem I actually give you, if I don't just tell you the radius is always 1/3 the height or something, you've got to figure out what's the relationship I can make between the variables that are in the thing he's asking me for. So in general, what do you try to do? You try to write an equation that's what I tell you, and you try to write the equation for what I ask you. If I don't really tell you anything directly except the situation, they did tell me the circle is in this little triangle is pregnant with a little circle. You draw that sucker. So they didn't tell you directly. They just gave you the idea, and you draw it, and you got to come up with all this other shit to get a relationship between these two variables. So the similar triangles here is what gives me the relationship between x and h. I need a relationship between the two of them because I got both of them in my stupid equation. I need to have one variable in there that I can actually work with. That's the more important idea than anything in this specific problem is, what is the formula for what I'm asking you to do something with? And then what's the relationship between if there's more than one variable in there, what's the relationship between them? I need to rewrite one in terms of the other one. I need one variable in the function I'm going to work with. Okay. This was not the best example. This is a pretty good one. I like this one, but I'm like, wow, that's some shit.
I'm a little confused about why it's h over x.
All right, so I made this statement. I want to see if anybody would say anything about why this is true, why these two are similar. What are similar triangles? What does it mean to be similar triangles? What's got to actually be the same in order for two triangles to be similar? The angles have to be the same. I like it. So my claim is there are angles that obviously this angle is the same in both. That's nice. So really and that angle is the same in both. This is right angle. It's amazing. So what's left to show then is that this angle is the same, and obviously it has to be. Why does that angle have to be the same? Well, if two angles are the same, all three have to be the same because they have to add up to 180. So that third angle has only one option. It's got to be that number. If that was 20 and that's 90, that's 110. That's got to be 70. And the same thing would have to be true for him. He's got a 20 and a 90. That would have to be.
Okay.
Do you guys get that? So that's, again, that's another little thing. I said they were similar. I wanted to see if anybody would say, why? But a lot of you guys are just like, sure, they're both triangles. That's similar. But the official definition of similar, the only way you can write a proportional relationship between the sides is if the angles are all the same. That means that one is a multiple of the other one. One is so many times bigger or smaller. That's why I can write this. That's when I can write a proportion. All right, I like it. All right, now, that one was a little more than I really intended it to be. I read it, I'm like, that sounds like the kind of problem I want them to do, and then, no, that's a little much. 57. So I'm saying, I'm not even going to worry about this problem, okay? Let go of that problem. I just want to show you the idea. There are some really good ideas there. They just went a little deeper than I really wanted to. All right. 57 says, this one is pretty straightforward. This one's remarkably straightforward. So they give you this velocity of a wave. Velocity of a wave of length L in deep water. Yes, that's how I pronounce water. L over C. Well, C over L. K and C are constants. So how many true variables do I have? Velocity is a function of 1. That's fantastic. Then I don't need them to tell me anything. And they just ask me, what's the length of the wave that gives the minimum velocity? Minimum. How would I start to attack that? Minimums occur one place. A minimum occurs where the derivative is 0. I like it. Or where it's undefined, right? So if I do dv dl. Now if I rewrite this a little bit, so this is k times L. Let me write this as 1 over c times L plus c times L to the negative 1. See, that's the ultimate best, all to the 1/2. There you go. That's the best way to write that. What's dv dl going to be? It's going to be k over 2. The 1/2 comes down. This whole thing is now to the and now the inside gets a turn. What's the derivative of 1 over CL? 1 over C. It's like me saying, what's the derivative of 5x? 5. What's the derivative of constant thing times L? Constant thing. What's the derivative of CL to the negative 1? Yeah, negative CL to the negative 2. I like it. Another mistake, I haven't seen anybody make this yet, but some people put a power up here, like a 1/2 powers. No. It's the inside. I'm ripping the inside out, and then I'm doing its derivative, right? There's no powers on that thing. It's really gross looking. Let's see. It's going to be k over 2 times 1 over c minus cl negative 2 all over the square root of L over c plus c over L. Sure. I like it. Yeah. So what are the critical numbers? Now, they tell you C and K are positive constants. So can this ever equal 0? L is the length of the wave. Well, that can't be negative. So positive plus positive can't be 0. So there's no critical numbers because there's a place where it's undefined. So I can focus totally on this thing. what's got to be true about this thing for there to be a critical number there? Has to be 0. The root of it has to be 0. That's the most fundamental place where critical numbers happen. So that means that 1 over c minus c over L squared has to be 0. That one doesn't have a lot going on. Multiply by L squared, multiply by c. So you get L equals c. Everything's positive, so I don't have to put plus or minus anywhere. So whatever this constant is, it actually represents the length of the wave that causes the velocity to be minimal. So if L equals c, this would be square root of 2. So square root of 2k would be the minimum velocity of the wave. That's neat. Okay, so sometimes the setup is not the difficult part. It's this wasn't even that difficult, to be honest, but sometimes it's the solving for where the critical numbers are. That's the difficult part. Ooh, yeah. Ooh, all right. What about this one? A metal storage tank with volume V is to be constructed in the shape of a right circular cylinder surmounted by a hemisphere. I love it. So can you draw that for me? What's it going to look like? Shape of a right circular cylinder. I like it.
Schwa, schwa, schwa. That's 58.
58, yeah. That's one of the ones I did, right? 57, 58, 59? Okay. So it's got to be surmounted by, it's only a hemispherical. That's so much better, Jeff. Looks like a pail now. So let me just put that on there. There you go. No, that's how you make. It's a circle. No, it isn't. It's a sphere. See? No, you never did that? No. Oh, I love the looks I'm getting. All right, it's somebody with one bad eye. Yeah. So they just tell me the volume is V. I'm trying to get the least amount of metal required. So what is it exactly that I am trying to minimize? I want the least amount of metal to make this.
Surface area.
Surface area. What's the surface area of half a sphere? And I'll give you these formulas because I'm not. Who remembers? It's really the derivative of the volume of a sphere, and you're like, well, that's nice. Something else I don't know. But you guys should really know the volume of a sphere. You should know this. 4/3 pi r cubed. If you take the derivative of that, it's 4 pi r squared, which is the surface area. It's crazy. So half a sphere would be 2 pi r squared. That's the surface area of a hemisphere. Now, what else do I have involved? What's the surface area of a cylinder? Do they tell me if it's... Yeah, so obviously, hopefully you understand, this is not going to have a top to it, right? This is the top to it, so there's not another thing here. So what's the surface area? What's the area of that circle on the bottom? The bottom? Pi r squared. Everybody cool with the fact that the sphere has the same radius, of course, because it's sitting on top of the sucker? Thank God. And what is the surface area of the surroundings? Does anybody remember?
2 pi r.
Yeah, 2 pi r, which is the circumference, times the height. This is going to be, you cut it, open it up, it's 2 pi r times height for the box that you make for the rectangle. Okay, so the total surface area is 2 pi r squared plus 2 pi r h plus pi r squared. So 3 pi r squared plus 2 pi r h. Now, how many variables are in that? Surface area is a function of how many variables? Damn. So what do we need to figure out? The relationship between what? The what now? The height and radius. Yeah, relationship requires two things. So height and radius. What is it they told me? They actually do tell me something. They tell me the volume is V. Very informative. But the volume is V. There you go. That's what it is. And what is the formula for the volume of this thing? I just told you what's the volume of a sphere. 4/3 pi r cubed. So what's the volume of a half a sphere? 2/3 pi r cubed. What's the... Oh,
Sorry. That's the volume for this.
for this tank.
Oh, for the whole.
That's the volume of the top. And then what's the volume of a cylinder? Pi r squared h. Which variable can you solve for easiest? H. If you said r, it's going to go show me. Yeah, I can solve for h because there's only an h that shows up. That's easy. I can get h by itself all day long. All right, so what would you get when you solve this for h? You get, so what they tell me, h is volume minus 2/3 pi r squared, r cubed, divided by pi r squared. So I can write it as v over pi r squared minus 2/3 r, looks like. Do you see that? Pi and r squared, two of them cancel. Looks like a much better way to write that. So I can plug that in there, and then I can do derivatives, because now I got it as a function of one variable, just the radius. So try to go a little further with that. Try to plug that in, take the derivative. Unless anybody sees something, has a question about what we've done so far. What have we done? Yes?
So you said the surface area of half a sphere is 2 pi r squared, right?
Yeah.
And then the surface area of the cylinder is 2 pi r h?
Yeah.
I'm just confused about why it's 3 pi r squared.
Oh, because then you got the bottom too.
Okay.
Another circle pi r squared. That's why it's 3. Yeah.
You said we'd be given the area formulas for the shapes shapes that are on the test?
Yes, well, yeah. The ones that I think you need. If you forgot the area of a triangle, you can come and ask me if you do that, right? But, I mean, I'm not going to assume that you know the surface area of a cylinder or something. We talked about it a couple times, but it doesn't mean it's in your head. Shit. Now I've got zombies in my head. It's in my head. Oh, yeah, cool. Now, I love you guys. There are no cookie cutter problems. There really can't. There can be. There are some cookie cutter problems, sure. But if you're desperately trying to make everything a cookie cutter problem, what do I mean by a cookie cutter? Like, I've never seen an example like this. Well, of course you haven't. And you're not going to have seen any examples like the one I give you in the test, except all the ones we've done. I mean, to be honest. So, what do I mean by that? I mean, the pictures you draw to work with on the test might not be like any of the pictures you had to draw for any other things, but it's the same idea. You draw the geometry of the problem, and you see what the relationship is between the variables. So you can replace one with the other one. Right? That's the idea. The idea doesn't change. I can't just give you the same problem with different numbers or something. Right? I know you want that. Even if I did that, there'd still be a lot of people getting it wrong. But I'm not going to do that. I got to test to see if you understand the concept, not do you understand this one application of the concept. All right, how are we doing here? We got surface area is 3 pi r squared plus 2 pi r times v over pi r squared minus 2/3 r. So let's clean this up a little bit. Here the pi dies, let's see, 2v over r minus 4/3 pi r squared, looks like. Yep. So then I finally end up with 9/3 minus 4/3 is 5/3 pi r squared, because these are like terms. Yay! Whenever you're taking derivatives, you try to decrease the number of terms you've got. So now I'm going to take the derivative. It's ds dr. So this will be 10/3 pi r minus, v is a constant. That's the volume they gave me, so don't freak out. Minus 2v over r squared. Have you done enough of those to see that? This is r to the -1, the negative comes down, it's to -2. Well, there you go. So one critical number is kind of silly. If r is 0, this is undefined, this piece, but could r be 0? If r was 0, it would disappear, right? So r can't be 0. So how do I get another critical number? Well, if I set this thing equal to 0, how do I go anywhere with this? How do I solve that? Definitely want to do one thing for sure. I would multiply by r squared, and I would also multiply by 3 just to kill the fraction. The other side 0 is going to eat it up. So I get 10 pi r cubed minus 6v, multiply by r squared, multiply by 3, equals 0. Divide by 2, it doesn't really matter. Now I can just get r by itself, right? Add the 6v, divide by 10 pi. All right, let me stop here for a second. Sometimes you get lost in the weeds and you don't focus on what's important. Right now, this is important, don't get me wrong, but this isn't really calculus. This is algebra. Right? I mean, this is just getting r by itself. So r cubed equals 6v over 10 pi, so it'll be 3v over 5 pi. And then just to cut to the chase, it's cube root. That's funky belly. So, I mean, if you know, now, do you have to make it exactly this to have a decent control on your cost? If you're trying to make a certain volume, and the shapes have to be like this, but it doesn't really matter the proportional if it's fatter or something. You guys kind of with me? Like it's a design aesthetic. It's like, I like a little like BB-8 robot with like maybe a little cylinder thing for my trash cans in my office. I want to be able to fit as much shit of these as I can. All right. Maximize the volume, make the shape this. So make the R a little bigger. This is the maximal R. If I can't work this into my assembly line constructing these things, I just make it the closest I can to this. And that's going to do pretty good. So I'm using the least amount of material to make the largest amount of space that can be used. That makes sense. So there's a lot of software out there that kind of does this kind of stuff automatically for you. You feed it a few parameters, that's what you're telling it, and then it works out what you're asking it to do. It does pretty much exactly this. Maybe. So that's the radius required. What is this? Let me see, 58. What did it say? What dimension? So how do I figure out the height? Just plug that sucker back in here. Cool. Who is it I was talking to? Watch, here's one little thing. See how I know r cubed really well? Let me just show you this one little thing. If I multiply top and bottom of this by r, do you see how r cubed shows up? Right? And I know what r is, plop, plop, and r cubed, I know what it is, plop. It's kind of like simplified a little bit ahead of time for me. That's one little tiny thing you notice what you're allowed to do. Why am I allowed to do that? Because r isn't 0, so I'm allowed to multiply top and bottom by r all day long. All right, that was 58. And then 59 is actually, 59 is after those problems. 59 should be really, really nice. Trying to maximize your revenue sounds like a good thing to do. Hockey team plays in an arena with a seating capacity of 15,000 spectators. With a ticket price set at $12. 11,000 people show up. A market survey indicates that for each dollar the ticket price is lowered, if cost lowered lowered by $1, then 1,000 more people will come. Holy shit. You start to see the balancing act here. I mean, this isn't too far off. In reality, in the real world, it's going to be a few more variables. They're not going to be so easily connected, but it's the same basic idea. For every so much changing in cost, what happens to the amount of people that get this or that come or that whatever, right? How should the owners of the team set the ticket price to maximize their revenue from ticket sales? So first off, in general, what would revenue really be? What are your unknowns here? There's two unknowns. The question is, how should the owners set the ticket price to maximize their revenue from ticket sales? But when you change ticket price, what else changes? Number of people, right? In fact, what's the revenue going to be? If they sold 1,000 tickets for $1 each, how much money do they make? $1,000. So if they sold 2,000 tickets for $3 each, they made $6,000. Well, how many tickets are they going to sell? I don't frickin' know. So let's call that X. Oh my God. And then the price of each ticket, let's call that, I don't know why you're spitting over there, Tim. Let's call it P just to be weird. So this we'll call X. The attendance we'll call X. And the price we'll call P. So then revenue is X times P. Now, how do I capture this whole, if cost is lowered by $1, then 1,000 more people attend? How do I capture that? For every, say again? Well, how many of these units am I going to change it by? Well, I mean, I could change it. If I lowered it by $2, then 2,000 more people will show up, right? Is the supposed way this works. You guys kind of with me? A little bit.
So is
So let's just see. So if my price was lowered by 1, then my attendance would go up by 1,000, right? Then it would be times X plus 1,000. But this is kind of supposing the answer already. This is saying let's lower it by $1. I don't know. Maybe I should raise the price, to be honest. Do you guys see that? I mean, raising the price could be an option here. You know, like, well, less people show, but you're charging them more money. So maybe there's a balance point the other way.
so the rate of change of the ticket price.
So let's see.
like
You ready? So my real variables here. X and P weren't the real variables. I just wanted to write the idea. And that's the way revenue normally is done, is the number of tickets you're going to sell times the price of each. Or the number of items times the cost of each, whatever they are. But what's the ticket price right now? $12. If I lower it, every time I lower it by $1, well, how many times will I lower it by $1? Let's say N times. And how many people are showing up right now for $12? 11,000 are showing up right now, but that's going to go up by 1,000 for every buck. Well, how many bucks did I lower it by? N. So this is going to go up by 1,000 N. So this is X number of tickets. Here it is. X number of tickets times P price. So the real variable is how much you're going to lower, the number of $1 steps you're going to take, which is going to be the number of